All right, good morning. It's Thursday, April 23rd, GEO420 Hydrogeology lecture. Okay, so today we are going to start getting some practice using pump test data to estimate aquifer parameters. And we're going to do this here mostly through an activity. So the first thing I wanted to do was to have you guys go to the Moodle site, and under week 14, here, let me share my screen here. Under week 14, there's going to be a Theis curve matching lab. And when you open that up, you'll see there's 3 or 4 files. See, I'm trying to share my screen here. Okay, so if you open up the Theis curve matching lab, there's 4 files. There's the actual lab. There is 2 data sets. That's the LQ23 drawdown data, the Theis data, and then there's a type curve. All right. So what we're going to do today is a type curve matching exercise. And so first thing to do is to download those 4 files. So get those downloaded onto your machine. Then let's open up a couple of these files. So I've already got this type curve estimation up. I'll make this a little bigger. And then I'm going to open up let's start off by just looking at this type curve here. Okay, so the type curve here is the Theis type curve. It's been, I made it with a program that just calculates the well function for a bunch of different values of U, all right? And so here's the plot of it's a plot of 1 over U versus WU. And it turns out that this plot is what the heads in a confined aquifer of infinite extent and constant thickness, so a Theis aquifer, this is what the drawdown would look like during a pump test, the basic shape of the drawdown. And it's a type curve because it's done in a dimensionless fashion, so that any set of well data that came from a Theis type aquifer would show this same shape. All right. So in the type curve methodology, what we're going to do is we essentially we're going to do a visual curve matching. So we're going to load into a image manipulation software. So I'm going to use PowerPoint. I think everybody should have access to PowerPoint. If you don't, any free image manipulation software will work. And what we're going to do is overlay our data on top of this curve and pick off some points. So let me go through. Let's go through sort of using the type curve with the first data set. So if you just kind of follow along, we're going to do the first part of the lab right now, or at least get you started on it. So I'm going to, I've got the files here. I'm going to open up a new PowerPoint here. I'm going to change the layout to be blank. And I'm going to load in first the type curve. So you can just drag and drop these into PowerPoint. And now I've got the type curve here in my PowerPoint. All right. So the next thing we're going to start off with is this file, welldata.png. All right, so let me tell you a little bit about this well data. This is synthetic data, or Theis data.png. This is synthetic data that I made basically following an example in the book. And so this is not real world data, but it gives us really pretty good data to work with and demonstrate the method. All right, so in order for this method to work, the first thing we got to do is get it so that our scales, the log distance between the scales, between these two figures is the same. So the way I do that is I take my data, I line up the lower bottom corner of the axes, and then I'm going to drag this upper right hand corner and get it so that the log scale intervals are the same. And this is kind of an iterative process because the way PowerPoint works, it doesn't anchor anything in one spot when we resize. So I have to keep kind of doing this process, but after a few times I get pretty close here. So right now my scales are the same. That is, between each log increment from each image, they are the same size. All right, and I'm doing this over 1, 2, 3 log increments, and so it's pretty good. All right, so now that's sort of the hardest part of this whole thing, getting that thing resized.
Does it matter that the points in the corner aren't the same?
It doesn't matter at all.
10 to the negative 1, 10 to the negative 3, and then the other one, it's 2 and 0.
Great question. Doesn't matter at all. The type curve is independent. The scales are independent of each other. The type curve doesn't matter. Essentially, the type curve will fit any set of data. And then we're going to use the fact that they're different scales here in a second. But the main thing is that they have the same log interval. All right, it doesn't matter the different numbers, just the length between one log cycle has to be the same. Okay, Now what we're going to do is visually overlay this thing and fit it to the data. All right, now we're going to have another lab where the computer is essentially going to do this same thing. And what we're going to do here is visually fit the data to our curve and figure out where they overlay the best. All right, so if I'm here, there's a gap between the curve and my data. If I'm over here, there's another gap. If I try to fit it down here, there's a big gap. All right, so your job here is with your eye to kind of figure out where on this screen do I have the smallest gap between my type curve and my data. All right, and I'm going to pick a point something like that. All right, so two things. When we do this visually, everybody's going to have a bit different of an answer. All right, if you do it mathematically, you'll end up at the same answer, but when you do it visually, everybody's going to have a little bit different of an answer. They should be close. All right, so you can fiddle with this thing and get the fit as best you can. Okay, now here's the point where we're going to make use of our axes. So I'm going to draw two lines. And the most important thing about these lines is that I have one horizontal line, and then I'm going to draw another vertical line. And they need to be perfectly horizontal and vertical. All right. The other thing about these lines is they need to be long enough to stretch across both axes. All right, and so the next part here is that we're going to pick a match point. And what I'm going to do is I'm just going to slide this line down until I see that it crosses two tick marks. So like right here, it's crossing a tick mark on my WU graph, and it's crossing a tick mark on my drawdown graph. So this would be a nice place here because I have two easy numbers to pick off. All right. Then the next thing I'm going to do is I'm going to do the same thing for the vertical line. I'm going to try and find a place where I cross two tick points if possible. So this looks like it's doing it right here. Okay, so my match point between these two graphs is now this the intersection here between these two lines. All right, that's my match point. And what I do is at this match point, I pick off the drawdown where this horizontal line intersects my drawdown on this axis. I pick off WU where it intersects the graph on this axis. All right, so here looks to me like this line is going across. This is 1, 2, 3. So my drawdown is 3 meters. And WU would be, well, this is 1 again, 2, 3, let's see, 1, 2, 3, 4. All right, now, any person will have a different visual fit. They can choose a different match point. The match point doesn't matter. It can be any place where these graphs overlap. All right? It's just where you've decided that you see a nice place to pick off even numbers. All right? You will pick off the S, the drawdown. You'll pick off WU from this horizontal line. From the vertical line, you're going to get little t, time, in hours, and 1 over U. All right? From those two graphs. Once you pick those off, all right, you can calculate the transmissivity of the aquifer from this equation. You need the pumping rate that I've given you up here. You've picked off your drawdown, little s, off the graph, and you've picked off WU off the graph. So with those three things, you can calculate aquifer transmissivity. All right. Similarly, you've picked off 1 over U, so you can figure out what U is. All right. You've picked off time from the graph here. You just calculated transmissivity, and I've given you the radius, so you can calculate your storativity. All right, so for the first part of the lab is just calculate the transmissivity and storativity of this synthetic data set. All right. So let's do this. When you guys, I'll be here. If you have questions, ask me. All right, because I promise other people are going to have, if you've got a question, then other people do, and it'll help. When you're done, what are we going to do when you're done? Well, when you're done, just let me know with this first part. And then we're going to talk a little bit more. We're going to lecture a little bit, and then we're going to do the second part of the lab. Okay? So there is some way to like put up an emoji on your screen, but I can't figure it out right now. But one way or another, just let me know that you finished so that I know we can move on. All right? Shouldn't take too long. I've done basically showed you the majority of it. It's just make your picks and then plug and chug on these equations. the Theis curve is the expected drawdown from a confined aquifer, all right, with perfect confining beds, so that the only water that we're pumping is coming out of storage from our confined aquifer, all right? So what we're going to do now is start talking about other types of aquifers and how those responses, how we see those responses in the drawdown. So we had, let's add another page here. And now we're going to consider a leaky confined aquifer. And I'm going to throw in the type curve here so that we can check it out. All right. So let's think about a situation now where we have, let me draw here let's draw, here's our land surface. We've got a confining layer here. We've got an aquifer. Oh. And beneath that aquifer, we have another confining layer. And we are pumping to a well, all right? And this well is screened over the full thickness of our aquifer. And we have an initial water table height in our aquifer. So our water in our well, it looks like this. Okay, so this is T equals to T naught. All right, this is our initial water table height. We start pumping water. What happens to the water height in our well?
Decreases dramatically.
All right, so the water height in the well goes down. All right. Let's call this T sub I. Okay, what happens to the water table away from the well?
Goes down as well.
Yeah, and there's a cone, right? So we've got this, let's call it at T sub I, we've got this sort of cone, a depression going down to our well, all right? So this is now the water table at T sub I. All right, so when we do that, we invoke radial flow. So groundwater's coming from our aquifer radially into our well. All right, and in the aquifer, you've got these horizontal flow lines. All right, and we, for a Theis equation, we're going to get, or for a pump test, we're interested in getting the transmissivity and storativity of the aquifer. Okay, so in a Theis, to get this curve, these beds are, this curve comes from these beds being completely impermeable. So they don't contribute any water to our well. But we could be in a situation here where this confining unit has a hydraulic conductivity of K prime. This one has a hydraulic conductivity of K double prime. This one has a thickness of B prime, and this one has a thickness of B double prime. All right, and when I drop the head in my aquifer beneath my confining unit, then I induce a vertical gradient in head, and I can get leakage or flow out of my confining unit and into the aquifer. All right, so I get vertical leakage. And an important point is I'm only getting vertical leakage where I have a drawdown cone. So this is vertical leakage. And I'll get that actually here as well. All right, so this vertical leakage is now another source of storage. So we can think about this as releasing storage. It releases storage. And then after some long time, it's no longer essentially the vertical gradient in our aquifer as this cone continues to expand out. So if we come out here to time, some other time, and the head here in our well is staying fairly constant, but now our cone of depression has expanded out, the vertical gradient here near the well has stayed the same. So we'll release storage at first out of this confining bed, and then as time goes on, we get to steady state leakage. All right, so in my drawdown, or in my drawdown curve, how this manifests itself is that during early times, before I start releasing water out of storage out of my confining unit, all right, or before it has sort of time to respond. So during very early times, my drawdown in almost all wells will typically follow the Theis curve. All right. Then I start to release water from storage out of my confining beds, and that's essentially reducing the drawdown. So anytime we have extra storage than just coming out of the confined aquifer, then I see lower drawdowns, and my curve will be beneath my type curve. All right? Then at some point, as my cone gets bigger and bigger and bigger, and I have stable gradients here, I'm going to start really releasing more and more and more water at a constant rate out of my confining units. And I'll actually start to really level off this curve, and it'll remain pretty flat. So I've got sort of three areas of response here. I've got the initial Theis. So I've got Theis response. Then I've got another response here, which is storage released from confining units. And then I've got this final zone here where I have steady state leakage from my confining units. Okay, so my curve has these sort of three distinct zones. The main thing here is that if I'm releasing storage from something other than just the confined aquifer, my curve will flatten off and I will get less drawdown than Theis would predict. All right, and we have equations that people have developed for this scenario. So in this case, my drawdown from a leaky confined aquifer where I'm releasing storage from the confining beds. So leaky confined aquifer with storage in confining beds. Drawdown is given by, so S, so Q, P, the pump rate, over 4 pi times the transmissivity. So this looks just like the first part of the Theis equation. Except now instead of the well function, I got this H of U beta. And H of U beta is now U to the negative, or to the infinity, not negative. E to the minus y over y. So this is the well function. This is the first part of the well function. This integral here is the well function, but we're going to modify it by this term beta root u over root y times y minus u dy. All right, so this is a new well form of the well function, and it is got the original part of the well function, this integral, but it's been modified here. And this beta is equal to r over 4 k prime big S prime. So that's the storativity. This is S double prime, and this is S prime. This is the storativity of these confining units. B prime T S plus, oh, this is the square root K double prime S double prime B double prime T S. And U is the same as we defined for the Theis function. So U is equal to R squared S over 4 big T little t. All right, so this now is the set of equations for drawdown in a leaky confined aquifer. All right, so let's have a little conversation here about these analytical solutions. So these are analytical solutions. This one is for a leaky confined aquifer with storage and confining beds. We'll talk about like one or two others, but let me just say this. There's a whole industry around defining different analytical solutions for different situations where you're pumping out of different aquifer configurations. We don't have time in this class to go over very many of them. And so what I would prefer is that you know sort of the Theis equation, which is the basis of most of these, and that you understand how the response looks different for different types of aquifer systems. All right. In this class, we're probably not going to use this equation. We're not going to use this equation. All right. What I want you guys to know is that there's a lot of different solutions for different settings. So if you find yourself working in a confined aquifer where you are seeing a response that's not fitting a Theis curve, all right, you would know that, hey, maybe we have leakage in a confining unit. And so we need to go into our book and find this equation and figure out how to use it. All right, that's my intention from this class, is not that you know how to apply each one of these different drawdown curves, but that you know what the signal looks like and you know that these other types of solutions exist that you can go and find and use at a later date. All right, so this is what I have when I've got storage in my aquifer, in my confined aquifer. What I want to do now is just look at what the curve looks like if there's no storage. So this is a leaky confined aquifer with storage in confining beds. Let's consider now what the curve might look like if we have a leaky confined aquifer with no storage in our confining beds. Oh, that's not what I wanted. So let's start off now with the Theis curve, all right? Now, when I have no storage, so no storage, what happens is I have the early time Theis response, but instead of having this period where I'm releasing storage and then I achieve steady state leakage, I basically go straight to steady state leakage. All right. So I've got early time response and steady state leakage. Early time Theis response. And then steady state leakage. The equation for this guy, drawdown, is equal to Q over 4 pi T WU R over B. All right. So a lot of these solutions have this form where we've got the pump rate over this 4 pi T, and then we put all the nasty stuff in this W or H or whatever function over here. So here U is the same thing that U always is. So U is equal to R squared S over 4 T T. B is T B prime, the thickness of our confining unit, over K prime to the 1/2. And W U R over B is equal to U to infinity e to the minus z minus R squared for B squared Z over Z dZ. All right, so here's just another, this is another analytical solution. For drawdown in a leaky confined aquifer with no storage in confining beds. Okay, so we have different responses depending upon sort of the processes acting in our aquifer. There's one more that I want to talk about, and that is unconfined aquifer, an unconfined aquifer. So let's let's talk a bit about an unconfined aquifer. So what are some of the ways that an unconfined aquifer is different from a confined aquifer?
Unconfined has the water table as the upper boundary.
Okay, so water table is upper boundary. What does that mean for the transmissivity of the aquifer?
Probably a lot greater.
It may or may not be greater, but how do we define transmissivity?
It's K times B.
And B would then change. It wouldn't be constant.
Ah, okay. So B changes with head in an unconfined aquifer. All right, so that's a biggie. All right, so water table as the upper boundary means variable thicknesses. That means as I draw my aquifer down, the thickness of my aquifer is changing. Therefore, my transmissivity is changing. What else is different about an unconfined aquifer?
Storage includes draining of pore spaces.
Okay, so storage, and this is a really important one. All right, we have two forms of storage in our unconfined aquifer. Remember, so storage in an unconfined aquifer is SY plus SS times B. All right, and this one is the same as a confined aquifer. This is expansion of water and compression of our porous material. All right, so, and then this one is drainage of pore space. All right, so these things make our unconfined aquifer look quite a bit different. Let's look at what this looks like, what an unconfined aquifer looks like on our Theis curve. So there's two things. There's one thing or a couple things that I want to talk about before I look at this. So the first is that this response, this expansion of water and compression of material, this happens at basically the speed at which a pressure wave can propagate through the subsurface. All right, so in geophysics, this is the seismic wave velocity. All right, and basically it's really fast. All right, so this happens, this storage is released at the speed a pressure wave propagates. All right, and if you're a seismologist, this would be the P wave velocity, VP, P wave velocity. And the bottom line is, this is fast. All right, so we release water from expansion and compression of the material rapidly. All right, as fast as the pressure wave can move through the aquifer, we start releasing storage. Now, this storage, the drainage of pore space, that happens at the physical speed at which we can move water through the pore space. So there, you got to bend your mind here a little bit. This one, just all that matters is that the pressure wave moves through the aquifer and it doesn't require the movement of water. All right. But this one, this form of storage requires the water to move. It requires the water to drain out of the pore space. All right. And so this happens, this is limited by fluid velocity. All right. And in a groundwater system, this is slow. Now, just a bit of verbiage in watershed hydrology or in hydrology, you'll hear this term for the speed at which a pressure wave propagates. See, a lot of watershed hydrologists didn't take seismology, and so they call this celerity. All right, and it sounds something like velocity, and it is the speed at which the pressure wave propagates through my porous media, all right, or through my hydrologic system. That's celerity. And then this, because it's drainage of pore space and it requires the fluid to actually move, it's moving at the fluid velocity. So celerity and velocity get thrown around a lot in hydrology, and celerity is the speed of the pressure wave, and velocity is the actual speed at which the water can move. And the bottom line is that celerity is really fast, and velocity or fluid velocity and drainage is really slow. So what happens then in an unconfined aquifer is I turn on my pump, I drop the water level in my aquifer. The first water that gets released is from this form of the storage because it happens fast. I immediately start expanding water and compressing my material. Eventually, as the head drops, the pores start to drain, and the storage released from drainage, vertical drainage, will start to show up. All right, so the way this looks in the type curve is, as you might be getting used to now, this early time response follows the Theis curve. All right, that's because during the early time, I'm releasing all my fluid from this same storage mechanism as a confined aquifer. But then, as time goes on, I start to drain pores out of my aquifer, all right? And I flatten the curve. All right, so here's my pore space drainage. Now, after a really long time, as my cone expands farther and farther, the change in head, so the amount of water that actually is coming out of vertical drainage gets smaller and smaller. So at late times in an unconfined aquifer, most of the storage that we can see, the storage response that we can see at the well, starts coming again from this Theis style response. And so we'll get this up curve. All right. So this one gets called the early time Theis. And this one gets called the late time Theis. And the one of the characteristics of an unconfined aquifer is this sort of S-shaped curve. So we're going up fast at the early time Theis. We flatten off as vertical drainage and specific yields start adding a lot more water. All right. And then at late times, when that gravity drainage is coming from farther and farther away, we get this late time Theis response. All right, so this S-shaped curve is the classic unconfined response. Now, one thing that is important is that these responses, all right, happen at different times. It is very possible that you can't run your pump test long enough to get to a late time Theis response in an unconfined aquifer. All right, in which case, it's really hard to tell the difference between an unconfined aquifer response and a confined aquifer with leaky confined aquifer with no storage in the beds. All right. And so what that comes down to is you understanding what scenario you're in, all right, and knowing which one of these solutions should be better. The unconfined response is really, there's an analytical solution for it. And it's really complicated. It's a function of a bunch of different parameters, and the curve matching is quite hard. One thing we can do, a cheat, we'll talk more about the analytical solution in class next week. But one cheat we can do for unconfined response is to basically modify my observed drawdown. And then use a Theis curve matching. So we're going to try that later, and we will try this because our Landquist data is probably from an unconfined aquifer. So we can modify this like this. We take and make this S prime. And this is from our observed drawdown. All right. And this is our observed drawdown. in an unconfined aquifer. And now we're basically accounting for the change in shape of the water table. And so this becomes our equivalent confined response. And now we can use Theis, say, curve matching to estimate T and S. All right. So we'll play with this next week. What we're going to do now is we're going to look at some real data in our lab. So this data set you've got that you have is LQ23 drawdown. This is from a pump test at the Landquist cross section of the Lolo Creek project. All right. And it's coming from what's probably an unconfined aquifer, just given the borehole logs in the area. So, you know, as part of your homework, you're going to construct some ideas of what these aquifers look like. And I think LQ23 is coming from an unconfined aquifer. So we'll look at the borehole logs, you know, later and make sure that. But what I want to do is just have a look at some real drawdown data and see how it compares to our type curve. All right, so the next portion here of the lab is to throw this data from the Landquist on our type curve. And you have to do the same process. So you load it in, all right? And then we got to get the scales to match. So the difference in the log units, or the distance between log units, needs to be the same. So I'm just going to iteratively keep trying to get these the same. They're close enough for now. All right, so what we can see here, if I try and match this data, all right, is that the shape of this curve is just not the same. It's very hard to get a good match. So part of what you're going to do today is think about how you would try and match this the best you can. All right. But we can also just throw the data on here and think about sort of early time Theis response. So if I play around with this, the curve is fitting on the Theis response for these just the first 2 data points. All right, super early time. The first, say, 10 minutes of this pump test are acting like a Theis curve. And then the data is falling off. So what kind of aquifers would this curve look like it could be coming from?
Could be a leak.
Be an unconfined aquifer or a leaky confined aquifer with no storage in confining beds.
Yeah, so either one of those would work here. All right. So here's a real world data set. This comes straight from Lolo Creek. You can see the signal of either a bunch of leakage from a very leaky confining bed or an unconfined response. All right. And now what I want you to do in this lab is sort of grapple with this idea that if you're going to use a Theis curve, you're assuming a confined aquifer. And so your job is to try and fit this curve to this curve. All right. And it's non-trivial to figure out how you're going to do that. All right. We do this kind of thing all the time in science where we have a model that isn't perfect and we're still going to try and get our best fit parameters. All right. And so here, you know, you're going to have to think about what the actual best fit parameters might look like. Where is the best place to put this curve so that you minimize the difference between these two? All right. And then you do the same process. You sort of pick your best fit point. All right. And then you do the same thing. You pick a match point and you pick off S, WU, and 1 over U. And this one, there's a lot of room for interpretation. You get to decide where you want to put this thing. You might say, well, look, I think just using the early time Theis response seems the best. Here's the problem with that. You're only fitting basically the expansion and compression of water and porous media. And so you're underestimating the storage. If you sort of fit the rest of the data, you should get a higher storativity and you're fitting more of the data. All right, so this is what the real world looks like. It's messy data that doesn't fit your easy model, and it gets worse than this. All right, and then next week we'll play around with letting the computer try and fit this bad model to the data and see if it can do any better. But B, we'll manipulate and try and turn this into the confined response. All right, so go ahead and, I'll be here for the next 20 minutes I'll just stay on the line and you guys can work on this lab. So what you need to do for the same of these is do the curve matching, pick your pick points, calculate transmissivity and storativity, and then turn those calculations. So turn in your lab along with your images and your calculations in via Moodle. And I think I said this was due next week, but I think we should try and get it done.
Can you repeat what you just said real quick about turning it in? Sorry.
Yeah, you just turn in. So what I would do is you can export this slide as I would do all my calculations and everything here on my PowerPoint. Then I would export my PowerPoint as a PDF, and you can load those PDFs into your Word file. And then you can turn in one file to the Moodle site on the Theis curve matching lab. All right, so you guys go ahead and get started, and then I'll be on the line from now, and we'll just stay on this Zoom meeting for office hours. So if you want to if it takes a little longer than the next 15 minutes or 20 minutes, then you've got extra time with me on the line. Sound reasonable? All right, I'm taking silence as yes.
Yes.
So I'm gonna pause recording and then I'll be on the line.